covering the topic of introduction to geothermal energy and future prospects. And just with that topic that we have, we will try to address some of the main subtopics in the content, which are there will be a small brief introduction to geothermal energy. I will then try to give you some examples of the uses and the applications of the geothermal energy in the current state. After that, we will be talking about a little bit about geothermal energy in the energy mix, and then we will be looking at the future of the geothermal energy. So we will do all of that by asking or answering those three questions. First one is a general question and encapsulates the geothermal energy content as well, which is why does renewable energy matter? And the second question will be for the geothermal energy and how it works, okay? We will try to figure out how the geothermal energy applications currently are done and the basic mechanism of behind that. And finally, we will be looking at a general spectrum or the conjecture of the future that renewable energy and geothermal energy holds. And we will be specifically talking about geothermal energy in this part. Before we begin, let me introduce myself as well. And I graduated from Middle East Technical University, Petroleum and Natural Gas Engineering Department in 2013. And from then to this day, I've been working for Zorlu Energy in the geothermal projects of the company. Currently, I've been acting as geothermal reservoir management and artificial lift manager of Zorlu Energy. And for the last 2 years, I also being giving lecture of the geothermal reservoir engineering in the two universities in the petroleum and natural gas engineering departments. So the very first question we need to ask about geothermal or the energy trend that holds the great potential is that renewable. And the question will be why renewable energy matters. So to answer this, we need to look at the needs of our work environments or the industrial applications. So as you know, energy is basically a currency of work. So if you have energy, you can turn it to work, and with that work, in any other process that you can think of, you can creating output, you can be creating some products to humankind to be used. And in this graph, you are seeing the total consumption of energy in the world, and you are seeing different trends starting from the early 18th centuries to 19th and after, and you can see a sharp increase in this 1950s, and we can easily say that we have some transition zones in those trends. And let's try to look at that graph in another way, which is that we can easily divide the sources of those energy consumption, okay? And in this graph, you can see different sources being identified or by their shares on that energy consumption. And as you can see, we have some remarks on those trends. First remark is in the very beginning of the 19th century, which is the start of mass production. And with that mass production, we know that one and actually two sources of energy was highly demanded, and still up to date they are also demanded, which are oil and coal. And this is where we began to use the fossil energy resources for the mass production we are doing. After that first trend, we are seeing another one in the middle of the 19th century to 1960s. And with that trend, we know that this is the time that we had the automated processes in the mass production, mass production mass production. So as you can see, with that automation era or the stage that we started, the oil and coal needs some support from the other resources, and which gives us to natural gas as well. And from that point to today, those fossil fuels, additional to some renewables as siders, was the main resources that we were using. And it is hard to say exactly what date we can put on it, but easily say we saw another trend after the 2000s or the millennia. So this was the Internet of the Things and the whole developed technologies that we are talking about or that we are looking for these days. And as you can see in this trend, there need to be another energy resources to support those fossil resources as well, because as you know, there are many concerns with the fossil fuel or the fossil resources being used for the energy production. Of course, the renewable part have or has own concerns, but still there needs to be some support to provide the energy that is demanded by the industry. So with that in mind, I believe that the next decades will be the years for the renewables increase in energy demand by that source. So basically, what I'm trying to say is that every era that we are known creates its own reality, and I think now we will be talking about an era that will be using mostly or depending mostly on the renewables. And this is why renewable energy and geothermal energy is important to our industries and our species. So at this point, with that covered, now we can focus on how geothermal energy works. And in here, we will start beginning with the basic components of the geothermal energy system, and then we will be digging into uses and applications methods. Okay, so for a general overview or a basic overview for the geothermal systems, any geothermal system that we are talking about, we basically need to define that four components you are seeing. First one is the heat source. Second one will be transfer path. And third one will be transfer media. And last one will be of course, the product. So in a general overview, every other geothermal system somehow have those four components. In some of them, in some of the geothermal systems, some of those components may be missing, but as we will see in the future of geothermal, now we are in a stage that we are also be providing that missing component to geothermal systems artificially. And for every other geothermal system, we have a geothermal fluid that that carry this energy to subsurface the surface to us being able to produce energy, any kind of energy from it, okay? So in that sense, we have several options in here. We could have some steam, just pure steam, in our reservoir, in our geothermal reservoir. We may have a brine, just the liquid phase, or we could have both of the phases in a mix as a mixture. And also, as I said, we could have some non-reservoir fluid as a geothermal fluid being used in the process. For the first three, that are the reservoir fluids, original reservoir fluids, it is highly dominated by pressure and the temperature, which will be the main geothermal or the which will be the geothermal fluid that we are using in our fields. So basically, uh, basically, according to phase diagram of the water, according to your reservoir pressure and the temperature values that you are working in, you are also you are also seeing that properties create your reality in terms of having a geothermal fluid, okay? And if we are looking for the heat source, as we say that the geothermal fluid will be the transfer path, and transfer media of our system, and this is the general overview of the heat source in different regions of world. As you can see, it is actually the surface heat flow values taken from different regions and making a distribution on all of the data. And as you can see, we have some abnormality zones in the regions seen here, and these are the regions that we are seeing those surface heat flows are uh, are above average values, means that in those regions or near those regions there will be some geothermal prospects as well. Of course, geothermal in many content in many contexts could be used as uh, heat heat energy or electrical energy in different applications. You can see all of those uses or applications, and depends on those applications, and an average geothermal heat flow or abnormality in here you are seeing could work for geothermal energy, because the needs of different systems are different. If you want to produce electricity, there will be a different energy demand from the system. If you will use a direct use application using as heat, there will be another, or there will be different energy demands. So it depends on those energy demands. It is possible to use geothermal energy in the regions which are having the average surface heat flow values as well. And today, as you can see from this pie chart, we are seeing we are seeing the countries having the geothermal install capacities at the moment. We are mostly referring on the electricity production side, because it is highly demanded use of geothermal energy, but we will be seeing other applications or other uses distribution over the world as well. In here, you can easily see that US is far ahead with the install capacity. And afterwards, we have Indonesia, Philippines, and Turkey. After that, we have New Zealand, Kenya, Mexico, Italy, Iceland, Japan, and here most of the companies have different stories. But as I'm from Turkey, and now I will also talk a little bit about geothermal in Turkey and the geothermal development in Turkey as well. So this is our geothermal development from beginning of the 1980s to today. And 1984, the first geothermal power plant was commissioned in Kızıldere geothermal uh, field in Turkey. And from that point to today, you can easily see how fast was that development. And now geothermal is as a key contributor to our energy production at the moment. Not that high, with not that high numbers, but it's a secure production resource in terms of electricity generation. So we had this development by actually the renewable or the renewal of the legislation in 2008 and 2009. So in these years, the government uh, had started to discuss, or had actually it was a little bit before that, but the result was in those years we had the legislation of the geothermal energy, and they had given a generous feed-in tariff uh, price for the geothermal energy production producers. And with that support from the government and that feed-in tariff mechanism, we have we have seen that geothermal investments were increased in a shortest time, and we have seen that nearly every prospect in known geothermal areas were commercialized by the companies. And from that point to today, the investments were somehow steadily increased. And after the first projects commissioned, more projects came by the uh, commissioned by the companies to provide that steadily increase in geothermal in Turkey. For for the as I said, for the electricity generation part, it is the popular or the high demand topic, but we know that geothermal energy is not all about just electricity production. It is a pure source of heat energy, and in any industry that you can think of, you need some kind of heat, or any processes that need heats in it. Geothermal energy provide that heat from the ground. So in here, we are seeing on the left side, this is the basically different showing different fields over the world, most famous fields. You can see the or Topo or Kızıldere in here, also Iceland in here. And we have some remarks on the every other field name. Those are the actually geothermal clay types. I will try to address this in the further slide, but just for now, we will be seeing those fields in here to address the different industrial use of geothermal energy. As you can see in the here, with the low temperature region, you have all the heating activities and direct use applications like this: greenhouse activities, fish farming, geothermal heat pumps, food processing, any other thing that you can think of can get a place in here in terms of needing needing heat to process something. Okay, and here with the lower or the upper region of the uh, temperature values or the temperature region, we are seeing electricity generation applications. And there are different applications in electricity generation as well. And again, I will be talking about the different systems and briefly give some information about every system in the next slides. But for now, it is important to know that according to your resource temperature, you are you are directing to some options of uses or the applications of geothermal from the natural state that you have the source. Okay, and and here we will be seeing those play types as stated for the every other geothermal field for the prior uh, map. And in here, you are seeing that there are two different types of geothermal plays. By the way, geothermal play means geological setting or general geological setting of the geothermal environment we are working on. So we have two different categories in here. First is conduction dominated, and second one is convection dominated. Here's an important thing to know. Mostly at the moment, all the commercialized geothermal fields mostly is convection dominated fields, because in those fields we have some advantages, conditions from the natural occurring structures. And we have three main type in here. First one is the extensional domain type. In this domain type, basically our heat source is able to come to the surface by the paths that is created by the extensional structures that is created in the field or the region. And the second part, we have plutonic and volcanic field type. And as you can see, for the volcanic field type, we have some intrusions, and those intrusions have heat, and that heat transfers to shallower sections, and with the fractures or faults that are already available at the region, we are having that heat to the surface. For the plutonic time, again, we had some intrusions at the time, and then after uh, after that, the rock absorbed that heat in it, and we are harnessing geothermal energy from that rock, because uh, that rock also heat ups to upper sections of the rocks that are that are present in the field. For the conduction dominated side, as I said, the convection part is favorable one, because the convection heat transfer process is much more faster compared to conduction dominated regions. But in conduction dominated regions, it is also possible to have geothermal energy, because, as I said, uh, depending on your application, heat demand or the energy demand will be different, and you can easily use conduction dominated fields for the direct use applications with the correct project planning and prospecting. Okay, and here we are seeing again all the possible applications of geothermal utilization methods in here, and this is a very great diagram to illustrate or summarize the geothermal application as well. In here, you are using geothermal fluid to produce electricity, and after you had produced that electricity, you still will have some remaining heat with that geothermal fluid that you have. So you are sending to some industries to use that heat in the processes. For example, fish drying, drying of the wood, or any other thing that you can think of. Again, you can use that heat in greenhouses, fish farming, and other low temperature applications. And after that, also uh, the lower temperature values you can use in the district heating systems, swimming pools, in some bathing lagoons for any other tourism activities or snow melting. And this example from Iceland. So they also could use this geothermal energy for the snow melting as well. And in here, I want to give another application or another example of this from our field. In our field, we have three different geothermal power plants. In one of them, which is called Kızıldere 2 geothermal power plant, we have this kind of integrated system. We are producing electricity from the geothermal fluid that we are gather from the wells. After that, we are sending our geothermal fluid to nearby greenhouses, and with that also we are providing water or brine to hot brine to nearby hotels to use in their spas. And addition to that, also we are heating a nearby province of Denizli in with the geothermal brine that we have after the process. And addition to all of those, also we have some non-condensable gases produced from the geothermal wells that we have. And we also sent these non-condensable gases to a nearby gas processing facility operated by Linde Gas, and they are processing our non-condensable gases and simply eliminate all the other gases than CO2, and they are using that CO2 in their industrial applications. They are using as dry ice, they are using for carbonated drinks and any other application. Okay, so as you imagine that we every other stage we are harnessing that geothermal resource for the different applications, and by doing so we are increasing our efficiency of energy use from the original source. Now we will be seeing different types of electricity generation systems. First, we will be seeing the flash geothermal power plants or the flash type geothermal power plants. In these power plants, you have some brine and steam mixture at the surface, okay? Not necessarily in the reservoir section, but at the surface with your given wellhead pressure, you have a mixture of steam and brine. So using that to use that steam and brine mixture, you are sending all the take the laser to point out easily. You send that uh, fluid mixture, okay, into a tank, basically a pressurized tank, which is called separator. In that separator, at a given pressure value or the temperature value, it will be parallel parallel with each other anyways. You are separating the gas and the liquid part of that geothermal fluid, and the gas part are sent to another equipment which is called demister. Basically, this equipment is trying to get as much as the uh, water or the liquid in the gas section, because this gas has a very high value of energy, and due to that energy it holds some of the liquid from the separation process, and in here we are eliminating those droplets of liquid as well, and afterwards it goes to this, follows this line and goes to turbine. And in the turbine, it expands with the pressure decrease. And with that expansion, it exerts force on the turbine blades. And that's causing the shaft to rotate. And that creates electricity in the generator. And you are connecting that electricity to the grid line in here. And liquid part is, after separation, directly goes into the injection wells and pump into the reservoir from those injection wells to support mass balance of the system. Okay, and in here we are seeing the other auxiliary equipments. First, we have ejectors or the vacuum system. There could be some vacuum pumps or any other equipments to make that service as well. In here, you are seeing that equipment because after the steam or the steam and gas gets into the turbine, after the generation, they have goes to another equipment which is called condenser. Okay, in this condenser, you have you have to turn the remaining gas to liquid form to use in the system, because as in the gas form you cannot use either steam or non-condensable gases. And as you can see in the condenser, you are using the gas goes into the condenser, and basically with a heat transfer system, you are turning that gas into the liquid. But as I told, we have some NCG from this geothermal liquid or the fluid. As it goes to the turbine directly, that gas also will be present in here, and we need to take that gas from the system, because as its name suggests, it is non-condensable gas. So we cannot condensate that in the condenser. So we need to remove that gas from the system. And to do that, we are using those ejectors or the vacuum pumps. For the ejectors, this is you are taking some of your steam with that high energy, high flow velocity, and goes to ejector, and the ejector creates a vacuum in here, and by that vacuum you are removing the NCG from the system. Okay, and after removing that, you are sending to another smaller condenser, which will be called steam condenser. And in here again, because as you use steam in the system, you mixed your steam for the creating vacuum with the vacuumed NCG gas, and again you are condensating your steam in here, and after that, with the little pressure that you have in here, you are emitting that gas into the atmosphere. And in here we have cooling tower. For the both processes, in the condenser processes, you need some water to cool down that gas in this condenser and to turn it to uh, liquid phase again. And for this, we are using cooling towers, and cooling towers basically circulating that water from taking water from the system, hot water from the system, cool down in the process. And there are two types of cooling waters, cooling towers. One is cooled by air circulating, and one other is cooled by uh, water circulating. In both of the cases, the main purpose and the working mechanism is same, but availability of water can change that design parameter. Okay, after every other process, if you have some additional cooled water in here, it is also diverted into the injection well and pumped to the reservoir to provide that mass balance. The second system, we will be seeing a binary geothermal power plant, which is basically suggests that we are using a binary fluid in the system to create electricity. In here, again, we could have some brine or steam mixture or just brine. It depends on our well head conditions, okay? But let's assume we have brine in this example. As you get that brine into system, you are using another another fluid to create electricity. It is because, let me just turn back to here again once more. As you are seeing here, there are region, mostly in this region we are using flash and dry steam geothermal plants. By the way, dry steam geothermal power plant is much like same with the flash, but in the reservoir section, you will be seeing just steam. Due to that fact, the separation station will be not present. And the other parts are very similar, okay? And as you can see, the highest range, you can only use these types of power plants because as the energy of steam in here will be much higher compared to these regions, you can easily use water vapor to produce electricity with the enthalpy that it has. Okay, but for the lower regions, the water vapor has energy that cannot efficiently convert to energy throughout a standard steam turbine. And in this section, you are using a fluid which has a lower boiling point that could create much more powerful, uh, steam or the vapor uh, in the lowest temperature regions. That's why we are using a binary fluid to produce electricity from those systems. Let's get back to the diagram. And you have that reservoir fluid in here, and this goes to evaporator. Okay, this evaporator is basically a heat exchanger, but it's just changed the phase of the liquid that or the fluid that goes into. And in here we have hot geothermal brine, and in the other section we are feeding this with our binary fluid to the system, and it heats up, creates steam of that binary fluid, and that binary fluid goes into the turbine. And these turbines are called organic Rankine cycle turbines, due to the fact that the cycle of that heat transfer is called. Okay, so that binary vapor goes into the turbine, exert force, and create electricity, and goes to the grid. From that, again, you have the condenser, and with condenser, you are turning that gas or the vapor of that binary fluid again into the liquid form by using water from the cooling tower, okay? And afterwards, you are sending that to a new equipment, which is called preheater. Again, preheater is a heat exchanger, which is, by the way, different than evaporator just by this. It is not changing the phase of that liquid. It heats up to the point that it could boil with a little input of heat. By dividing into two stages, you are using this geothermal fluid afterwards in the preheater, creating additional efficiency in here, okay? And after that, first in the evaporator, then it goes into the, after the absorption in here or the heat transfer in here, it goes into the preheater and give the remaining heat to the liquid phase of the binary fluid. And after that heat transfer, the remaining water goes into the injection well pump to the reservoir from there. Okay, system is somehow similar to flash system, but in here we are not using geothermal fluid in the turbines to create electricity, produce electricity. In here again, as I said, for the dry steam, there isn't any separation station because you have pure steam. Just you are using a demister to remove that droplets, and after that, this process is all the same with the flash power plant. You have ejectors to remove non-condensable gases. You have condensers to condensate the remaining gas after the heat transfer or the expansion in the turbine. You have cooling tower to cool down all the processed water. You have steam condenser to eliminate the gas in the last stage of the production. And you have also brine injection pumps and the injection wells to support your pressure in the reservoir. And here, by the way, we have also some hybrid systems, okay? And mostly those hybrid systems using flash type power plants with binary type power plants. For example, in our geothermal fields, we are using some kind of that integrated systems. As you can see here, we have some remaining heat in here, okay? Because we have some gas, we have still have some degree of heat energy in here, and also we have some heat energy in here. According to your design, let's assume that you had separated at a very high pressure value at a very high pressure value of your geothermal fluid. It means that it will have also a higher energy content in it after the separation in the liquid form as well. If you want to use that, you can easily incorporate a binary power plant from this section, okay, and use the different systems in here. Maybe you can use the same cooling tower, for example. But as you can see, the condenser or the turbine is different than the steam one, so you need to use other those systems separately. But you can incorporate or integrate a binary power plant from this part of the line, and you think of this line goes to evaporator because it is the same content. It only depends how much energy remaining that you have after the separation, okay? And also for the steam phase, it is an option to take into consideration because you could have a great amount of steam, and due to that fact, you could have great amount of energy in here, and you can maybe you cannot use that steam energy in the steam turbine, but you can transfer that heat to a binary fluid and use in this ORC cycle, okay? So that being said, also another orientation could be using some multi-stage separation points as well. For example, you have some high pressure separation in here. With that, you had some content, some rate of steam, which could be a little bit lower, but the energy will be higher compared because you are separating at a higher pressure, okay? And afterwards, you could also incorporate another separation station to create more steam. It will be at moderate flow rates, but also it will have moderate enthalpy values. And for example, if you have a great resource that can easily fit in third stage of separation as well to produce more steam, to produce more electricity. Of course, you can use just one stage which is corresponding to all of those, but as you take the bigger steps on that separation part, the equipments that are using needs to be bigger, and alongside the other design criteria, the spatial demand or the spatial need of your facilities will be another issue with that approach. And in here, we are seeing that different power plant types, we have different regions which will be much more efficient compared to other methods. Of course, this graph is created by the data from the different power plants which are already commissioned and producing. So the data has some bias on that matter of fact, but again, it is easily summarizing the situation as well, because as you can see on the lower section, we have better we have better performance for the binary side, because as I said, in the lower sections, steam turbines tends to give poor performance compared to a low boiling point fluid, okay? And in the upper sections, we are seeing great efficiency from the double flash power plants, as I called multi-stage power plants, okay, multi-stage flash power plants. And also you are seeing that dry steam plants has higher efficiencies on the higher enthalpy values, because in those regions you have only steam in the reservoir section. Due to that fact, dry steam power plants is the only option that you can think of, okay? So basically, in here and the information from the prior slides, we can easily say that with that geological setting, with that reservoir conditions, our use of or the methods of using geothermal energy in that region is already directing us to a place. Okay, for example, if you have some volcanic regions, and it most probably will have some high temperature values on the reservoir sections. Due to that fact, you may have some steam dominated reservoir, and due to that fact, you will be you will be better choosing a dry steam power plant or flash power plant to produce electricity. Because if you try to use direct use applications in terms of using geothermal energy as a heat, in that process, you will be missing the opportunities that region or that field give to you. On the other hand, if you are trying to produce electricity from the, let's say, a conduction dominated field with very average surface heat flow values, then it will be waste of energy and money in terms of project feasibility. Okay, and here we are seeing a geothermal project life cycle, which is also the main problem, we can say, with the geothermal, or the main risk with the geothermal. As you can see, in the beginning, we have very high risks due to uncertainties in the underground, because as we have so many data from the surface observations or the surface measurements from we could have some geothermal manifestations on the region as geysers or the fumaroles or any other steam or hot brine could be present at the regions naturally. But again, it is just having just those manifestations is not enough. So we need to address those uncertainties from the beginning. And with that, you can see that with the exploration stage, with the activities that we are doing with the seismic surveys or the magnetotelluric surveys or any other geological mapping or the activity in the field is going under this stage, address the lowering risk of the first stages of the geothermal project. And in here also the investment by the either from the public or the private resources are a little bit suspicious about the project itself. And after the first tests and the first drillings, now you have a solid or some sort of data that is solidly gives idea of your resource in terms of project feasibility and producing heat or energy, and you are now trying to figure out that resource and how to use it properly. And in here, you are decreasing your risk, but again, we will be seeing a cost associated to it. After that, for the feasibility studies and the field development, construction, and the startup part, it is a little bit steadily movement compared to first stage. And as you can see, it is steadily decreasing over time until the operation and maintenance part of the project. And again, cost will be at the highest point when these steps are done. And in here, disadvantages think to every other geothermal project or every other geothermal field is that due to this high risk zone in the earlier stage of geothermal project, now geothermal energy is losing some place compared to other advantages it has. Okay, so it is a big decision making parameter for the investors, because you will be seeing a high risk at the very beginning of the project. It means that it will be more, it will be costing more for the investors at the very first stages. But after that region, the operation and maintenance part, we will be seeing advantageous part of geothermal energy in the further slides. And in here, we can we saw that how renewable energy is important to us. Okay, and we try to summarize different applications and geothermal systems in general. And now we can ask the question of what is the role of geothermal energy in the future energy outlook, okay? And try to imagine what future holds for the geothermal energy. And in here, we will be seeing two different data, okay? And on the left side, you are seeing the countries. As I said, we saw the electricity generation part, and we are now looking for the direct use applications. And in here, again, China, Turkey, Japan, Iceland, Hungary, and other countries holds great amount of energy. But I want to emphasize that if you can easily read that, these all values excluding heat pumps, okay, heat pump applications, and just try to remember, and maybe just we can go back to numbers in here, okay. As you can see, we have just 16,000 megawatts, okay, of electricity production. Let's get back into the direct use. In here, we have okay, 30,000 megawatts. We have almost twice as much of those production with the direct use applications. And in here, we are using different direct applications, okay? And in here, we are seeing also heat pumps as well. As you can see, if you sum all of these numbers, you get half of this number as well. So it means that heat pumps is much more greater use of geothermal energy at the moment. And this is an important thing to understand, because as we try to use geothermal in direct use applications given in here, including heat pumps, okay, it is much easier and much efficient compared to electricity generation. Because as we turn to another slide of ours, okay, in here, as you can see, we have surface heat flow values of different regions, and we have some abnormality in regions, okay. And if we say on average, we could easily calculate for an average rock type or average formation, okay, or a generic formation. We can calculate an average heat flow value, and let's assume that it sits here, okay. And above that, it means that we could have some geothermal potential. If you look at like that, you are not seeing this region in most of the regions occupied by humankind, okay. So, but if you take this average and go for the lowest range, the region or the area extent is much higher. That means on the lower side of those applications in here, okay, direct use applications, you could have a wider regional application area, and also means that it will create a greater market for the geothermal use, or the investors or the companies that will be a party of that market. Okay, so that means geothermal direct use will be much more important compared to electricity generation, because actually for now it is already important if you compare the numbers. Okay, and and for the heat pumps, it is very good system, because of course there are some discussions about this heat pump applications is either geothermal energy or geoenergy, some arguments or some discussions going around like that, but it is not important. At the end, it is a resource that we can use, and we can adopt in our future energy needs. Okay, and in here you are seeing a basic application in the winter time. There, you are using these heat pumps to take the heat from the ground and heat up to your household, or the on the summer side you can use the colder regions in the ground to remove the heat from the house as well. Okay, and this is basically a heat exchanger again, which was we have seen in the binary power plant applications. With that basic heat exchanger, you can both heat up the well or cool down the well in all seasons. And for direct use and heat pump side is aside, we have another great opportunity in geothermal. As from the first slide related to the components of the geothermal energy, I said that with the current technologies or the current advancements, we are able to replace some of those components artificially at the moment. And this is done by EGS systems, enhanced geothermal systems. And in those systems, basically, you could not have a transfer pad. You can create it. You could not have a geothermal fluid, and you can replace it with a non-reservoir fluid and use to produce electricity. In EGS applications, there are several different categories. Some of the studies are concentrating on the just heat transfer in the underground sections of the well, okay, or the reservoir sections of the well. You are just and for example, wellbore heat exchangers or the systems similar to like this are trying to produce electricity from just that heat transfer, conduction heat transfer. And in some applications, they are more radical. They are creating fractures. They are connecting wells with each other with those fractures and creating those surface areas to create greater heat transfer. And with that heat transfer, they are using some non-reservoir fluids to harness heat from the reservoir section, from injector to producer well. And at the surface, they are using these heat energy to produce electricity or direct use in the different applications. And in here on the left side, you are seeing the potential of, on average, or the general overview of the conventional field direct use applications. Okay, in the x-axis we are temperature. We have temperature. In in the y-axis, we have that. And as you can see, we also seeing that average gradient of geothermal gradient. And above that, we have direct use applications in a small region, okay? And we have a very high region for the conventional hydrothermal systems that we have seen in the prior slides, and we have a greater potential in the EGS region as well. So it means that with the EGS, as you can extrapolate this temperature axis into higher sections, and as I said, in the higher sections, due to high energy that you have in the resource, either it could be in the steam or the non-reservoir fluid, you will be having much more potential to produce electricity from that resource. With that in mind, for the future of geothermal, there are three advantages that we have compared to disadvantages with the high risks starting of the projects. Geothermal is basically a baseload, means that you can use this energy in every other season, every other hour of the day without any interruption. For the wind and the solar, this is somehow different. As you know, if you don't have any wind or sunny sun time, then those power plants will be not available for the producing electricity. But for geothermal, it is not like that. 7 to 24, you are having that geothermal resource in your mix, okay? Second thing, with the direct use applications and the heat pumps and all other industrial applications, geothermal needs will be much less in terms of heat value of the resource. It means that you will be using widespread on the regions that, even though that has not geological advantages. Okay. And lastly, we have deep potential with the EGS and the other applications, meaning that for the deep potential regions, or in general for the deep applications, the electricity generation or the heat created will be much more than compared to conventional systems, meaning that the investments on those projects will be much feasible if we somehow find ways to decrease those uncertainties and decrease the upfront costs related to drilling and the exploration activities. With that, that's all from my take. And if you have any questions to ask, I would be glad to answer. Thank you for your attention.